Look up on a clear, moonless night far from any city, and if your eyes are sharp and the sky is dark enough, you will see a faint smudge just above the constellation Andromeda, a soft, elongated blur, so subtle that for most of human history it was mistaken for a cloud, a nebula, a wisp of gas drifting through the heavens. It is not a cloud, it is not gas. It is a galaxy containing 1 trillion stars, each of them a sun, many of them older than our own, and it is moving toward us at 110 kilometers per second, faster than any bullet ever fired, faster than any spacecraft ever launched, fast enough to cross the entire continental United States in the time it takes you to blink. It has been falling toward us for billions of years, and in approximately 4.5 billion years, it will arrive. Not pass by, not graze us. Arrive in a collision between two of the largest structures in the known universe. A collision that will reshape everything, that will last 1 billion years, that has already begun, and that will, in a very real sense, determine what the night sky looks like for every civilization that might ever arise on the other side of it. If you enjoy videos that take the largest events the universe produces and make them legible, that convert the language of astrophysics into something you can hold in your mind and feel the weight of, I'd genuinely appreciate it if you hit back. Like button and subscribe. It helps more than you know. Now, settle in, get yourself nice and comfortable. Let's begin. The most common misconception about this event is that it is a catastrophe. People hear galaxy collision and picture two vast structures of stars slamming into each other like freight trains, a universe-scale demolition derby in which suns are shattered, planets are vaporized, and everything is reduced to debris. That picture is not just incomplete, it is wrong in almost every particular. Not wrong in the way that an approximation is wrong. Wrong in the way that saying the Atlantic Ocean is basically a puddle is wrong. Wrong about the nature of the thing, not just its magnitude. A galaxy collision is one of the most constructive, creative, generative events the universe produces. It builds things. It births things. It transforms two structures into something grander than either was alone. Understanding why requires understanding what galaxies actually are, what they are mostly made of, what separates the stars within them, and what collision means when the things colliding are almost entirely empty space. The Milky Way is a disk of stars, gas and dust, roughly 100,000 light-years across, and about 1,000 light-years thick at its edges, bulging to perhaps 16,000 light-years thick at its central bar. It contains somewhere between 100 billion and 400 billion stars. The precise number is genuinely uncertain, because we are inside it and cannot see through the dust and gas that fills the galactic plane. It is, in effect, a city whose inhabitants have never seen it from the outside, trying to count its buildings from street level in a dense vault. Our best estimates, refined over decades of infrared observations that penetrate the dust, put the stellar count at around 250 billion. 250 billion suns, most of them accompanied by planetary systems, distributed through a disk that takes light, the fastest thing the universe allows, 100,000 years to cross. Now consider the distances between those stars. The nearest star to our Sun is Proxima Centauri at 4.24 light-years. 1 light-year is approximately 9.46 trillion kilometers, 9,460 billion kilometers. So the nearest star to us is roughly 40 trillion kilometers away. If you shrank the solar system, the Sun and all its planets out to Neptune, to the size of a quarter, a coin you can hold between your fingers, the nearest star would be, at that scale, roughly 800 kilometers away. Not meters, not kilometers down the road. 800 kilometers, the distance from London to Edinburgh and back again. Travelled 3 times over at that scale. The solar system is a quarter. The nearest star is 800 kilometers distant. The galaxy is a collection of 250 billion such quarters, each separated from its neighbours by 800 kilometers of empty space, all of them orbiting a common centre in a vast, slowly rotating disk. This is what galaxy means. It means almost nothing. By volume, a galaxy is almost perfectly empty. The fraction of the Milky Way's volume actually occupied by stars is roughly equivalent to the fraction of the volume of a large concert hall occupied by a few dozen grains of sand scattered across it. When 2 galaxies collide, the stars almost never hit each other. The stellar grains of sand, flung through the collision at high relative velocities, pass through the other galaxy's stellar distribution with essentially zero probability of direct stellar collision. Not because the stars are nimble enough to dodge, but because space itself is so vast that even a trillion-star galaxy is, from the perspective of its own contents, mostly nothing. What does collide, violently and consequentially, is everything else. Galaxies are not merely collections of stars. They are complex multi-component systems in which stars are, in some ways, the least dynamically important component. The gas, the hydrogen and helium and dust clouds that permeate the interstellar medium, filling the spaces between stars, is not empty, is not thin. It is a fluid, and fluids collide in ways that solid objects do not. When 2 galaxies interpenetrate, the gas clouds of each galaxy slam into the gas clouds of the other. Unlike the stars, the gas cannot simply pass through. Gas collisions are inelastic. They dissipate kinetic energy as heat. They produce shocks, supersonic compression waves in which gas is compressed and heated to millions of degrees in millions of degrees. They trigger gravitational instabilities in the compressed gas that cause it to collapse into dense clumps. Those clumps are the seeds of new stars. Entire stellar populations, thousands, tens of thousands, millions of new stars are born from the gas compressed and shocked and destabilized by the collision. The galaxy merger is, in a very real sense, a stellar nursery. The collision creates stars, many of them, all at once, in a burst of star formation that can outshine the combined ordinary luminosity of both galaxies by a factor of hundreds or even thousands. These events, merging galaxies undergoing massive collision-triggered star formation, are called starburst galaxies, and we observe them throughout the universe, bright beacons in the infrared sky, burning with the light of newly minted suns. But before we trace the full arc of what will happen when the Milky Way and Andromeda meet, we need to understand how we know it is going to happen at all, and why, for most of human history, we did not even know that Andromeda was a galaxy. The story of how humanity came to understand galaxies is one of the great intellectual journeys in the history of science, and it is worth tracing because the misconceptions are instructive. For most of recorded history, that faint smudge in the direction of Andromeda was known as a nebula, the Latin word for cloud or mist, one of dozens of fuzzy patches in the night sky catalogued by astronomers as curiosities. The largest of these, M31, the 31st object in the catalogue compiled by Charles Messier in the 18th century, who was a comet hunter cataloguing things that were not comets so they would not confuse him, was visible to the naked eye on a dark night, and had been noted since at least the 10th century by Persian astronomer Abd al-Rahman al-Sufi, who described it in his Book of Fixed Stars as a small cloud. It was a cloud in his conception, as it was in everyone's conception for the next 1,000 years. a local nebulosity, a nearby thing. The true scale of the universe was not understood until 1924. In that year, Edwin Hubble, working at the Mount Wilson Observatory in California, using the 100-inch Hooker telescope, then the largest telescope in the world, resolved individual stars in the outer regions of M31. Not just any stars. He found Cepheid variables, a class of pulsating stars whose period of pulsation is directly related to their intrinsic luminosity, making them what astronomers call standard candles. A standard candle is a light source whose intrinsic brightness you know, independently of distance, which means you can measure its apparent brightness, how bright it looks from where you are, and calculate how far away it must be to appear that dim. The further away, the dimmer. The relationship is precise and well established. Hubble measured the periods of the Cepheids in M31, determined their intrinsic luminosities, compared them to their apparent brightnesses, and got a distance. The distance was somewhere around 900,000 light-years, far outside our own galaxy, then understood to be perhaps 100,000 light-years across. M31 was not a nebula in our galaxy, it was a galaxy in its own right, separated from us by a gulf of space larger than the entire Milky Way. The universe, in the span of a single observation session and a careful mathematical analysis, became hundreds of thousands of times larger than it had been the day before. The island universe. Hypothesis. The idea that the nebulae were in fact independent galaxies comparable to our own, scattered through an immensity of space, was confirmed. The modern picture of the cosmos was established. And once M31 was established as a separate galaxy, we now call it the Andromeda Galaxy, after the constellation in whose direction it lies. Its motion relative to us became a natural object of study. Measuring the radial velocity of a galaxy, how fast it is moving toward or away from us along the line of sight, is done through the Doppler effect. Light from an object moving towards you is shifted toward shorter wavelengths, bluer. Light from an object moving away is shifted toward longer wavelengths, redder. By measuring the precise wavelengths of known spectral lines, the characteristic colours emitted and absorbed by specific elements in the light from Andromeda, and comparing them to their known rest frame wavelengths, astronomers determined that Andromeda is blue shifted. It is moving toward us, not away. Toward, at 110 kilometers per second along the line of sight. But before we use those numbers to calculate a collision time, let us spend a moment with Andromeda itself, with what it is, how it compares to our own galaxy, and what its own history reveals about the nature of the encounter ahead. Because Andromeda is not just a mirror image of the Milky Way, it is a different galaxy, with a different past, different properties, and a different character. And understanding those differences helps us understand what the merger will produce. Andromeda is larger than the Milky Way in almost every measurable sense. Its stellar disk spans approximately 220,000 light-years, more than twice the diameter of the Milky Way's disk. It contains roughly 1 trillion stars, compared to our 250 billion, give or take the large uncertainties on both estimates. It is more massive. The total mass of Andromeda, including its dark matter halo, is estimated at perhaps 1 to 1.5 trillion solar masses, compared to the Milky Way's roughly 800 billion to 1 trillion solar masses. The uncertainties in these mass estimates are large. Measuring a galaxy's total mass requires tracing the motion of objects at its outermost edges, where the orbits are slowest and hardest to detect. But the consensus is clear. Andromeda is the dominant galaxy of the local group, and the Milky Way is the second largest. When these two meet, the encounter is not between equals. It is between the largest and the second largest structures in our cosmic neighbourhood. Andromeda also has a more chaotic and merger-rich history than the Milky Way, at least in the relatively recent cosmological past. It has a prominent extended halo of stars, a diffuse cloud of stellar material surrounding the main disk that extends to remarkable distances, well over 1 million light-years from the galactic centre in some directions. This halo is not primordial. It is the debris of previous mergers. Smaller galaxies that fell into Andromeda over the past few billion years were torn apart by tidal forces and scattered their stars through the surrounding halo in arcs and streams that are still visible today. The Andromeda Galaxy has numerous stellar streams in its halo: the Giant Stellar Stream, the Northeast Shelf, the Western Shelf, all of them the shredded remnants of satellite galaxies that Andromeda has already consumed. Met 32, one of the bright satellite galaxies of Andromeda, visible as a compact companion, is thought to be the dense remnant core of a once larger galaxy that Andromeda partially absorbed billions of years ago. Andromeda, in this sense, is already battle-scarred. It is a galaxy in the middle of an ongoing process of hierarchical assembly, growing by consuming its neighbours, and the Milky Way is simply the largest neighbour that has not yet been consumed. Andromeda also has two supermassive black holes, or rather, a double nucleus. The centre of Andromeda, when observed with the Hubble Space Telescope, shows two distinct brightness peaks, separated by roughly 5 light-years. The leading explanation is that Andromeda has one supermassive black hole, estimated at 50 to 100 million solar masses, but the stellar disk that surrounds it is eccentric, so that the stars spend most of their time near the apoapsis of their elliptical orbits around the black hole. The concentration of stars near apoapsis creates a bright peak that is offset from the black hole itself, producing the double nucleus illusion. Whatever the precise interpretation, Andromeda's central black hole is between 12 and 25 times more massive than the Milky Way's Sagittarius AB. In the eventual merger, this asymmetry matters. The more massive black hole will dominate the final merged system, and Sagittarius AB will, in effect, be swallowed by Andromeda's central black hole, growing the merged object to somewhere between 54 and 104 million solar masses.
Now, the dark matter. Every discussion of galaxy collisions must grapple with the fact that the dominant component of a galaxy, by mass, is invisible. Dark matter, whatever it is, a question not yet resolved despite decades of searching, makes up roughly 85% of the total matter in the universe, and it dominates the mass budgets of galaxies. The Milky Way's dark matter halo extends perhaps 300,000 to 600,000 light-years from the galactic centre, 3 to 6 times the radius of the visible stellar disk, and contains perhaps 600 billion solar masses of invisible material. Andromeda's dark matter halo is comparable. Together, the dark matter halos of the two galaxies already overlap at our current separation of 2.5 million light-years. The dark matter of Andromeda is already exerting a gravitational pull on the dark matter of the Milky Way, and vice versa. The merger, in this sense, began in the dark matter long before the stars became involved. Dark matter is cold, meaning its particles move slowly compared to the speed of light, and it interacts only through gravity. Unlike gas, it does not collide. Like stars, it passes through itself in a gravitational sense, with individual particles following trajectories determined by the combined gravitational potential of all the other dark matter. But unlike the stars, dark matter is distributed in a diffuse, roughly spherical halo rather than a rotating disk. And when two dark matter halos overlap and merge, they do so through a process of dynamical friction and violent relaxation. Just like the stars, but on a larger scale and over longer timescales. The dark matter halos of the Milky Way and Andromeda will merge first. They are already beginning to merge, and the merged dark matter halo will then gravitationally guide the subsequent stellar merger, providing the gravitational scaffold within which the stars, gas, and supermassive black holes play out their own dynamics. 110 kilometers per second is, by everyday standards, an unimaginable velocity. It is roughly 400,000 kilometers per hour. A commercial aircraft travels at about 900 kilometers per hour. Andromeda is closing in roughly 440 times faster than a commercial jet. The entire distance from the Sun to the nearest star, 4.24 light years, 40 trillion kilometers, would be covered in slightly over 11 million years at this speed. That sounds slow until you remember that the current separation between us and Andromeda is approximately 2.537 million light years. 2.537 million years of travel, even for light. At 110 kilometers per second, closing that gap takes roughly 4.5 billion years. But there is a subtlety. The 110 kilometers per second is the radial velocity, the component of motion directly toward us along the line of sight. For a long time, astronomers did not know the transverse velocity, the component of motion perpendicular to our line of sight, the sideways motion. Without the transverse velocity, you cannot know whether the collision will be head-on, a glancing blow, or a near miss. This measurement required the Hubble Space Telescope to make, and it was finally accomplished in 2012. By tracking the precise positions of stars and Andromeda over several years and measuring their tiny proper motions, their apparent movement across the sky, the research team led by Roland van der Marel at the Space Telescope Science Institute determined that Andromeda's transverse velocity is small relative to its radial velocity. Small, but not zero. The upshot is a clear, quantitative prediction. Andromeda and the Milky Way will collide. Another near miss? No, research team led. No, a direct collision in approximately 4.5 billion years, followed by a merger that will take another few billion years to complete. The precise details of the collision depend on initial conditions, on the exact masses and velocities of both galaxies and their halos that are known with some uncertainty. This uncertainty feeds into the collision timeline, the geometry of the first encounter, and the number of subsequent passes before the final merger. But to navigate this uncertainty, astrophysicists run not one simulation of the merger, but thousands, ensembles of simulations, in which the initial conditions are varied within the range of uncertainty, tracking how different initial conditions lead to different collision outcomes. The simulations are computationally intensive. Modelling 1 trillion particles over billions of years requires the kind of supercomputer time that was unimaginable a generation ago. But modern computational astrophysics has made them routine. The ensemble of simulations produces not a single prediction, but a probability distribution over outcomes. The collision happens with certainty, but the precise timing has an uncertainty of perhaps 500 million years in either direction, and the geometry of the first encounter varies across the ensemble. What the simulations agree on is the broad outline. The merger proceeds through a sequence of passes. The two galaxies interpenetrate, separate, fall back together, interpenetrate again, and gradually coalesce. The total time from first contact to final merger is 6 to 8 billion years. The starburst associated with the merger is triggered by gas compression during the passes. The final product is a massive elliptical galaxy. The supermassive black holes merge after the galactic cores merge. These outcomes are robust across all the simulations, regardless of the precise initial conditions. One of the most important inputs to these simulations is the dark matter halo of each galaxy, its mass, its radial extent, and its density profile. The dark matter halo determines how much gravitational drag each galaxy exerts on the other as they pass through each other. The darker halo provides the potential well that the other galaxy's stars and gas must climb out of after the first pass through, and the energy lost in climbing that well determines how tightly the two galaxies are bound after the encounter. A more massive dark matter halo means more energy lost on the first encounter, a shorter return time for the second encounter, and a faster overall merger. The best current estimates of the Milky Way and Andromeda halo masses put the merger time at approximately 4.5 billion years to first contact, and a total merger duration of roughly 6 billion years, though this could easily be 5 to 7 billion years. Depending on the precise halo masses, the uncertainty is not in whether the merger will happen. It is only in when we have some rough masses, and where we cannot, in when will lead to a long sight. The uncertainty is not the case. The collision will not happen all at once. That is the first thing to understand about the timeline. Galaxy mergers are not events. They are processes, billion-year processes in which the two galaxies interpenetrate, separate, fall back together, interpenetrate again, and gradually lose enough energy through gravitational interactions to coalesce into a single object. The whole sequence, from first contact to final merger, will take something like 6 to 8 billion years from now. To put that in context, the entire history of complex multicellular life on Earth spans roughly 600 million years. The Milky Way Andromeda merger will take 10 to 13 times as long as the entire history of animal life on Earth to complete. The first close approach, first contact between the outer halos of the two galaxies is already underway, in a sense. Both the Milky Way and Andromeda are surrounded by vast, tenuous halos of hot gas and dark matter that extend far beyond the visible stellar disk. The dark matter halo of the Milky Way may extend for hundreds of thousands of light years in every direction, and Andromeda's is comparable. These halos are already overlapping. The gravitational influence of Andromeda is already felt in the Milky Way's outer reaches, subtly distorting the trajectories of the most distant stars, warping the edges of the stellar disk in ways that have been observed in surveys of the galaxy's outer structure. The interaction has begun. It is just that the timescales involved are so enormous that begun means something different from what it means in ordinary language. We are, right now, in the earliest, most glacially slow phase of the encounter. The first dramatic moment, the moment when the visible stellar disks of the two galaxies begin to pass through each other, is approximately 4 to 4.5 billion years away. 4 to 4.5 billion years. For comparison, the Earth is 4.54 billion years old. The event we are describing is as far in the future as the formation of the Earth is in the past. Single-celled life did not exist on Earth 4.54 billion years ago. The moon had only recently formed from the debris of a giant impact between the proto-Earth and a Mars-sized body. The continents did not exist. The oceans had only just condensed. We are talking about a time span that encompasses the entire geological, biological, and evolutionary history of our planet, all of it, as the interval between now and the moment the merger begins in earnest. This matters because it should calibrate your sense of urgency. The collision is not coming soon by any human measure, but it is coming with certainty. The mathematics of gravitational attraction admits no alternative, and tracing what will happen is not speculation. It is the application of well-understood physics to a well-characterized initial condition. We know what we are dealing with. We know how galaxies merge because we can observe mergers happening throughout the universe. The universe is so vast and old that at any given moment, some fraction of the galaxy population is in some stage of merger, providing us with a kind of evolutionary sequence of snapshots. We can see galaxies just beginning to interact, their outer halos overlapping. We can see galaxies in their first pass-through, two disks crossed at odd angles, tidal streams of stars flung out by the encounter. We can see galaxies in the chaotic multi-pass phase, their structures distorted beyond recognition. We can see recent mergers, their two nuclei still distinct, but spiraling toward coalescence. And we can see the end products, massive elliptical galaxies, smooth and featureless, the stellar orbits randomized by 1 billion years of gravitational chaos into a settled, round distribution. Each of these is a frame in a film that our own galaxy will one day live through. Let us trace the film, frame by frame. Long before the first contact of the visible disks, something more subtle and more beautiful is happening: the tidal distortion. As Andromeda draws closer, its gravitational field, not uniform across the Milky Way, but slightly stronger on the side of the Milky Way facing Andromeda than on the far side, begins to pull the Milky Way stars asymmetrically. The same differential pull that causes tides on Earth's oceans, caused by the Moon's gravity being stronger on the near side of Earth than the far side, operates on the galactic scale. The stars on the Andromeda-facing side of the Milky Way are pulled slightly more strongly toward Andromeda than the stars on the far side. The result is a tidal distortion, a stretching of the galaxy's structure in the direction of Andromeda, a faint asymmetry in the distribution of the outermost stars, a gentle warping of the disk's edge. We already observe warps in the Milky Way's outer disk that are partly attributable to the gravitational influence of the Large Magnetic Cloud, one of our smaller satellite galaxies. The influence of Andromeda, still distant, is subtler, but it grows with every passing million years. There is a profound irony in the observation of these precursor effects. We are watching, right now, the earliest tremors of a collision that will not reach its first dramatic climax for 4.5 billion years. The warping of the Milky Way's outer disk, visible in surveys of distant stars conducted with telescopes like Gaia, carries within it the gravitational fingerprint of Andromeda's approach. It is like watching the bow wave of an enormous ship, still tens of kilometers distant, begin to rock your boat. The ship is not here yet, but its influence has already arrived. The Milky Way, its outermost stars subtly tugged out of their expected orbits, has been feeling Andromeda's gravity for millions of years, without knowing, without any observer inside it being able to say with certainty which particular asymmetry came from Andromeda and which from the Large Magellanic Cloud or other nearby structures. The precursor signal is real, but hidden in the noise of other gravitational influences. It takes the most precise telescope ever built, Gaia, measuring stellar positions to a few micro-arcseconds, to begin to tease it out. As the separation decreases to roughly 1,000,000 light-years, still 3 times our current distance from Andromeda's apparent location in the sky, the visual transformation of the night sky begins in earnest. Andromeda grows. Not from week to week, not from year to year, not from century to century. The timescales are too long for any individual observation to register the change. But across thousands of generations, across millions of years of accumulated change, the smudge grows, it brightens, it takes up more sky. At 1,000,000 light-years, Andromeda would subtend roughly 10 degrees across the sky, about 20 times the angular width of the full moon. Visible to the naked eye as a structured oval of faint light, its central bulge clearly brighter than its outer disk, its overall glow a dominant feature of the night sky in the direction of Andromeda. At 500,000 light-years, 40 degrees, a significant fraction of the entire sky, a glowing oval reaching from horizon to near horizon in a single direction, the individual stars of its outer regions beginning to be resolved by the naked eye under the darkest conditions. The sky, at this stage, no longer has a single galaxy in it. It has 2. Our own, the Milky Way band still arching overhead, and this newcomer, this approaching Leviathan, filling the sky ahead like the prow of an incomprehensible ship. At the moment of first contact, when the stellar disk of Andromeda and the stellar disk of the Milky Way begin to spatially overlap for the first time, Andromeda will span a substantial portion of the entire sky. Its central bulge will be among the brightest objects in the heavens, comparable in surface brightness to the Milky Way's own central bulge, visible towards Sagittarius. The sky, from any planet in either galaxy, will be extraordinary in a specific way, not bright in the way of noon sunlight, but structured, complex, detailed, filled with luminous streamers and arcs and concentrations of light that correspond to the stellar populations of the approaching galaxy, overlaid on the familiar band of the home galaxy. The first contact moment is not an explosion. It is a slow, geological timescale interpenetration, beautiful and vast and entirely indifferent to the observers it illuminates. Now consider the physics of that first pass-through more carefully, because the details are as remarkable as the spectacle. As Andromeda's disk passes through the Milky Way's disk, the relative velocity of the 2 galactic disks is several hundred kilometers per second. The combined approach velocity, now much faster than the initial 110 kilometers per second, because the gravitational attraction has been accelerating both galaxies toward each other for 4.5 billion years. At 110 kilometers per second, at a separation of 2.5 million light-years, conservation of energy and angular momentum dictate that by the time the galaxies are separated by only, say, 100,000 light-years, comparable to the Milky Way's diameter, their relative velocity will have increased to something like 500 to 700 kilometers per second, in the same way that a falling object accelerates as it falls. The first pass-through occurs at these speeds. At 600 kilometers per second relative velocity, the crossing time of one galaxy through the other is roughly the diameter of the Milky Way divided by the relative velocity, 100,000 light-years divided by 600 kilometers per second. Converting units, 100,000 light-years is about 9.5 times 10 squared, 0 meters, and 600 kilometers per second is 6 times 10^5 meters per second. The crossing time is therefore 9.5 times 10 squared 0 divided by 6 times 10^5, which is about 1.6 times 10^15 seconds, roughly 50 million years. The first pass-through takes approximately 50 million years to complete, from the moment the leading edge of Andromeda contacts the leading edge of the Milky Way to the moment the trailing edge of Andromeda clears the trailing edge of the Milky Way. 50 million years. the most powerful natural event our galaxy will ever experience, the first contact with another galaxy of comparable mass, lasts as long as it took for mammals to evolve from tiny insectivore-like creatures in the immediate aftermath of the incessant asterisk impact that ended the Cretaceous period, to the first appearance of whale-like animals in the Eocene oceans. It is a geological epoch. It is brief by galactic standards, but it is not instantaneous. At this stage, hundreds of millions of years before the first close approach, the night sky as seen from Earth, or from whatever planet might exist in our solar system at that time, would look essentially unchanged. The faint smudge of Andromeda, visible to the naked eye now as a patch the width of 6 full moons, would appear somewhat brighter, somewhat more resolved, as the distance shrank. If you were watching the sky from the surface of a planet over millions of years, compressing geological time into a film, as we can do with simulation, you would see Andromeda gradually brightening, gradually growing, its oval shape becoming clearer and more detailed. It would be the most spectacular object in the night sky by far, many millions of years before the galaxy's first touch, glowing with the combined light of a trillion stars, a luminous oval, occupying an ever larger slice of the sky, the most ominous and beautiful phenomenon visible from any vantage point in the universe. By the time the first close approach arrives, approximately 4 billion years from now, give or take some uncertainty in the exact timeline, Andromeda will fill a significant portion of the sky, not as a disk of clearly resolved stars to the naked eye, but as an enormous, luminous, structured glow, visually dominating the sky in its direction, the central bulge bright enough to cast faint shadows, the spiral arms stretching across dozens of degrees of arc. The Milky Way's own band of stars would still be visible as our galaxy's disk still surrounds us. But the dominant visual feature of the sky would be this approaching Leviathan, swollen with the light of a trillion suns, growing night by night, year by year, though on timescales imperceptible to a single human lifetime, or even to many consecutive human generations. The first pass-through is violent in the gravitational sense, though utterly imperceptible to any individual observer living through it. The two stellar disks interpenetrate. Stars from Andromeda pass through the volume of space occupied by the Milky Way, and vice versa. No stellar collisions occur. The stars are too sparse, the probability too low. In fact, astronomers have calculated that the expected number of direct stellar collisions during the entire Milky Way-Andromeda merger is approximately 0. Not approximately 1, 0. The uncertainty in that estimate is such that some small number of collisions, perhaps a handful, out of a combined stellar population of merely 1 trillion, might occur near the centers of the two galaxies, where stellar density is highest. But in the disk, in the outer regions, where most stars live and where our sun resides, nothing touches anything. The stars flow through each other like two interpenetrating swarms of gnats, each gnat too small and too far from the others to collide, even when the swarms fully overlap. What does happen is this: the gravitational interaction between the two galaxies is not between each star and each other star. Gravity doesn't work that way at these scales in any significant individual sense. What matters is the large-scale gravitational potential. Each galaxy exists in the gravitational field of the other. As the galaxies move through and past each other, the changing gravitational field, sweeping through the galaxy like a tide, not steady but dynamic, changing as the galaxy's relative positions shift, pulls stars off their normal orbits. It flings stars outward. It creates what are called tidal streams, long arcing ribbons of stars, stripped from their parent galaxies and sent on looping, eccentric orbits that curve away from the main galactic bodies. These tidal streams are beautiful things. We observe them around other galaxies undergoing mergers, and we observe them in the Milky Way itself. The Sagittarius stream is a vast ribbon of stars being stripped from the Sagittarius dwarf galaxy, one of our smaller satellite galaxies, currently being absorbed by the Milky Way, and it wraps around the entire sky in a great arc. The Milky Way Andromeda merger will produce tidal streams on an incomparably grander scale, arcs of millions of stars flung out over hundreds of thousands of light years. The visible signatures of gravitational violence operating on the largest scale a single event can span. And what of our own sun? Where does it end up? This is not a single word for anyone, but for the non-Jew read and learn what time she can be. Sound always with blue sky. The Sun is currently located in the outer third of the Milky Way's disk, roughly 26,000 light-years from the galactic center, orbiting with a period of about 225 million years. During the first close approach, the Sun could find itself anywhere along its orbital trajectory. Depending on the precise timing and geometry, it might be in the part of the Milky Way that is most strongly perturbed by Andromeda's passage, or it might be on the far side, less affected. Computer simulations of the merger have tracked millions of test particles representing possible solar positions throughout the collision, and the results reveal a probabilistic answer. There is no guarantee that the Sun remains in the Milky Way's main body during the merger. There is a small but non-zero probability, some simulations put it in the range of a few percent, that the Sun is flung into the outer reaches of the merged galaxy in a tidal stream, displaced from its current orbit by many tens of thousands of light years. More likely, it ends up somewhere in the diffuse outer region of the merged system, orbiting at a larger radius than it does now, its orbit altered but not catastrophically so. What the simulations agree on is that the merger fundamentally randomizes the orbital structure of most stars. The regular, nearly circular orbits that most disk stars currently follow, the organized co-rotating structure of the spiral disk, will be destroyed. Stars that once moved in elegant, nearly circular paths around the galactic center will find themselves on elongated, tilted, chaotic orbits that take them through all parts of the merged galaxy. The kinetic energy of the two galaxies' orbital motion, the energy in their approach and first pass through, gets redistributed into the random motions of individual stars, a process physicists call violent relaxation. In violent relaxation, the fluctuating gravitational potential of the chaotic merger phase scatters stars to random energies, distributing them in orbits that collectively produce a smooth, roughly ellipsoidal distribution, the characteristic shape of an elliptical galaxy. Two disk galaxies, through merger, transform into one elliptical galaxy. Not immediately, over billions of years, but inexorably. After the first pass-through, the two galactic cores, the dense central regions of each galaxy, each containing a supermassive black hole, will have moved past each other and will be separating. But they cannot separate indefinitely. The gravitational attraction of each galaxy on the other has removed kinetic energy from the system, kinetic energy that went into the tidal streams, into the violent relaxation of stellar orbits. And the two cores, having lost energy, cannot quite escape each other, They slow, they stop, they fall back toward each other. The second collision comes, perhaps 1 billion years after the first. Then, after a shorter interval, a third. Each successive pass-through is less energetic, the two cores losing more kinetic energy each time, spending more time close to each other, until finally, after multiple passes, perhaps 4 or 5 over the course of a few billion years, they no longer separate at all. The two galactic cores spiral toward each other, driven by the remaining gravitational energy of the combined system, and the two supermassive black holes, the Milky Way's Sagittarius A bat with 4 million solar masses, and Andromeda's central black hole with perhaps 50 to 100 million solar masses, begin their own in-spiral toward a final merger. These are the most massive black holes in our cosmic neighbourhood. Sagittarius A dot contains 4 million times the mass of our Sun, 4 million suns compressed into a region smaller than our solar system. The Andromeda black hole is between 50 and 100 million solar masses. Their eventual merger will be an event of extraordinary violence, one of the most energetic events since the Big Bang, at least in our local universe. The in-spiral of the two black holes will take millions to hundreds of millions of years after the galactic cores merge, because the black holes must lose angular momentum and energy to eventually find each other. This energy loss occurs partly through a process called dynamical friction, the gravitational drag experienced by the massive black holes as they move through the dense stellar environment at the merged galaxy's center, scattering stars and losing momentum with each interaction, and eventually, in the final tight stages of the in-spiral, through the emission of gravitational waves. But before the final in-spiral, long before the two black holes are close enough to emit significant gravitational waves, there is an intermediate period that will transform both of them and the surrounding galaxy in spectacular fashion. Both Sagittarius A dot and Andromeda's central black hole are, at present, remarkably quiet. Sagittarius A dot is one of the least active supermassive black holes known. For its mass, it is extraordinarily dim, accreting material at a rate roughly 1 million to 1 billion times below the theoretical maximum. It occasionally flares. Astronomers observe brief brightenings in X-ray and infrared emission, lasting minutes to hours, when a cloud of gas or a disrupted asteroid falls into its vicinity, but these flares are modest by quasar standards. The Milky Way has no active galactic nucleus. It is not a quasar. It is not even a safe-Earth galaxy, the class of moderately active galactic nuclear one-step allo quasars. It is quiet, cold, dormant. The merger will change that as the two galaxies interact and the gas in both galaxies is shocked, compressed, and driven toward the galactic centers. The accretion rate onto both supermassive black holes will increase dramatically. Gas that would have spent millions of years drifting in the interstellar medium, never coming anywhere near the galactic center, is funneled inward by the gravitational torques of the merger. Large quantities of cold gas, the fuel for both star formation and black hole accretion, will flow toward the center, feeding both the starburst and the supermassive black holes simultaneously. During the most active phase of the merger, both black holes may undergo episodes of rapid accretion that light them up as active galactic nuclei, AGN, emitting copiously in X-rays, ultraviolet, and even radio wavelengths. Powered by the energy released as infalling gas is heated to millions of degrees by friction and compression before crossing the event horizon. An AGN outburst from Sagittarius AB would be extraordinary from any observer's perspective within the Milky Way, or rather it would have been extraordinary if observers were present, since any biologically complex life on Earth will be long extinct by this time. At its peak activity, a Sagittarius A act, accreting at even a small fraction of its Eddington limit, the theoretical maximum luminosity for a black hole of its mass, set by the condition that radiation pressure equals the inward pull of gravity on infalling matter, would be visible in the night sky as a bright point source, not as bright as the full moon, not blinding, but visible to the naked eye from Earth's former location, a concentrated point of blue white light at the galactic center, where previously there was only the diffuse glow of the galactic bulge. An AGN. A miniature quasar, powered by the collision-driven feeding of Sagittarius AB, broadcasting across the galaxy in hard radiation, driving winds of energetic particles outward into the surrounding medium, potentially suppressing star formation in its immediate vicinity through sheer radiative heating. The two AGN, one from each galactic nucleus, would coexist during the multipass phase of the merger, both flaring as gas is driven toward them, both potentially illuminating each other's host galaxy from tens of thousands of light years away. We observe double AGN in merging galaxies throughout the universe, systems like NGC 6240, a luminous infrared galaxy in the constellation Ophiuchus, in which two X-ray bright nuclei, separated by roughly 3,000 light-years, are both accreting material as their host galaxies merge around them. NGC 6240 is what Milkomeda will look like during the multi-pass merger phase, when both galactic nuclei, both hosting active, accreting supermassive black holes, are still distinct but approaching. We are not imagining a future scenario. We are looking at it right now, in another galaxy, 400 million light-years away. Eventually, the two nuclei merge. The two supermassive black holes find themselves within a parsec of each other, within about 3 light-years, and the gravitational wave in-spiral phase begins. The last few thousandths of a parsec are covered in gravitational waves. The two black holes, each distorting space-time around them, orbit each other ever faster, ever closer, radiating space-time ripples with increasing amplitude and frequency until they touch and merge in a millisecond of violent coalescence. The merged black hole rings like a struck bell, oscillating and emitting a final burst of gravitational waves, the ring down, before settling into the quiescent, slowly rotating configuration of a Kerr black hole, Milkomeda's central black hole, between 54 and 104 million solar masses, the product of a 9 billion year sequence of galaxy formation, stellar evolution, merger, starburst, AGN activity, and gravitational wave emission. After the merger, the central black hole may briefly accrete at high rates as the remaining disturbed gas settles toward the center, producing a final AGN episode. Then it quiets. The gas is consumed. The starburst has ended. The supernovae have heated and dispersed the remaining cold gas. Milkomeda's star formation rate drops towards zero. The galaxy red dense as its young, massive, blue stars age and die, while no new ones replace them. The elliptical galaxy settles into the slow, quiet life of the red and dead. A massive, metal-rich, stellar population-rich system whose era of active evolution is largely complete, whose future will be defined not by violent events, but by the slow cooling of stars and the occasional accretion of a passing dwarf galaxy that briefly rekindles a spark of star formation. before being absorbed and digested. The gravitational waves emitted by two supermassive black holes, spiraling together, millions to hundreds of millions of solar masses, separated by distances measured in astronomical units, orbiting each other with periods of years to centuries, are not the high-frequency gravitational waves that LIGO and Virgo detect. They are low-frequency waves with wavelengths of light years, produced over timescales of years to millennia. They're precisely the kind of gravitational waves detectable by pulsar timing arrays, the galaxy-scale detectors I described in our neutron star discussion. And they are precisely the kind of signal that pulsar timing array collaborations in 2023 found evidence for in the stochastic gravitational wave background. Somewhere in the universe, right now, pairs of supermassive black holes are spiraling together, producing gravitational waves that wash through the galaxy and subtly shift the arrival times of pulsar pulsars. Our own future black hole merger, Sagittarius A, become with Andromeda's central black hole, perhaps 8 to 10 billion years from now, will be among the loudest gravitational wave sources in the local universe when it occurs. The final merger of the two black holes will release in gravitational waves an energy equivalent to millions of solar masses converted entirely to radiation, emitted in what is called the ring-down phase, the period immediately after the two black holes merge, when the newly formed larger black hole oscillates and radiates away the distortion in space-time it inherited from the asymmetric merger, settling into the smooth axisymmetric shape of a Kerr black hole. This event will be brief and violent and invisible in any electromagnetic sense, detectable only through the space-time ripple it sends outward. It will reshape the local gravitational landscape of what is then called Milky, the merged galaxy, and whatever civilizations exist to detect it, if any do, will have the unprecedented experience of watching two supermassive black holes become one in real time through the vibration of space-time itself. But let us not leap so far ahead. Let us return to the collision process and examine what happens to the gas, because it is the gas, not the stars, not the black holes, not the dark matter, that produces the most spectacular observable consequences in the immediate aftermath of the first pass-through. The interstellar medium, the gas and dust distributed through both galaxies, is the reactive component of the system. When the two disks first interpenetrate, the gas clouds of the Milky Way encounter the gas clouds of Andromeda at relative velocities of hundreds of kilometers per second. The gas cannot pass through. It collides, compresses, shocks. In the shock, temperatures rise to millions of degrees. The compressed heated gas radiates intensely in X-rays, lighting up the merger zone with hard radiation. Simultaneously, the compression creates density enhancements, pockets of gas denser than the surrounding medium, and where density exceeds a critical threshold, gravity takes over. The gas fragment collapses under its own weight. A protostellar cloud forms. Stars ignite. This is the starburst, a dramatic, collision-triggered acceleration of star formation in which the galaxy pair produces stars at a rate many times higher than either galaxy achieves in isolation. To understand how dramatic this starburst can be, compare the normal star formation rates of the two galaxies. The Milky Way currently forms stars at a rate of roughly 1 to 3 solar masses per year, 1 to 3 suns worth of new stars every year. Andromeda forms stars at a somewhat lower rate currently, having experienced its own starburst in the relatively recent past. Together, in quiescent conditions, the two galaxies produce perhaps 2 to 4 solar masses of new stars per year. During the collision-triggered starburst, this rate can increase by factors of 10, 100, or in the most extreme cases, 1,000. During the peak starburst phase of the merger, the combined galaxy might be producing hundreds of solar masses of new stars per year, hundreds of new suns every year for millions of years. Over the course of the starburst, which might last 100 million years, the merger event produces as many new stars as there are stars currently in the entire Milky Way. These new stars are not evenly distributed. They form in dense clusters, in giant molecular cloud complexes, in regions of particularly high gas density along the collision front. The result is a galaxy that, during the merger phase, looks completely unlike either of its progenitors. Instead of the elegant spiral arms and relatively uniform stellar population of a disk galaxy, the merging system, called an irregular galaxy, or sometimes a train wreck galaxy. It shows chaotic knots of intense star formation, loops and arcs of tidal debris, regions of brilliant blue-white light from millions of massive newly formed stars, and dark lanes of dense gas and dust, threading through the whole structure. We can look at photographs of similar mergers happening elsewhere in the universe and see this with our own eyes. Right now, the antennae galaxies, NGC 4038 and NGC 4039, roughly 45 million light-years away, are two spiral galaxies in their first pass-through, their tidal tails extending for hundreds of thousands of light-years, their overlap region blazing with starburst activity. The mice galaxies MGC 4676, the Whirlpool Galaxy and its companion M51b, the Cartwheel Galaxy. Each of these is a snapshot of a different moment in the merger process, and each shows us something of what Andromeda will look like at that stage. There is a consequence of the starburst that operates on a completely different timescale, and that has profound implications for the long-term fate of the merged galaxy. The most massive stars, those with masses 10, 20, 50, 100 times that of our Sun, live brief, violent lives. A star 100 times the mass of the Sun burns its fuel so furiously that it exhausts its nuclear reserves in a mere million years, compared to the 10 billion years our Sun will spend on the main sequence. A million years is nothing. It is about the same interval that separates modern humans from our genus Homo's first stone tool makers in East Africa. These massive stars end their lives in core collapse supernovae, the same cataclysmic events that produce neutron stars and black holes, and that scatter heavy elements through the galaxy. A starburst that produces millions of massive stars is also producing, with a delay of a few million years, millions of supernovae. The energy injected into the interstellar medium by millions of supernovae, each releasing roughly 10,444 joules of kinetic energy into the surrounding gas, enough to outshine the Sun for millions of years, is enormous. It heats the gas. It dries outflows. It pushes material out of the merged galaxy's center, sometimes forming galactic winds that carry metal-enriched gas out into the halo and even out of the galaxy entirely. These galactic winds are not gentle breezes. In the most powerful starburst galaxies, galactic winds blow outward at hundreds to thousands of kilometers per second, carrying with them the heavy elements forged in the starburst's supernova cascade. Carbon, oxygen, silicon, iron, all the elements built in the brief, furious lives of massive stars, scattered by their deaths, carried on the wind into the halo and the intergalactic medium. These elements, enriching the gas that will eventually reaccrete onto Andromeda or disperse into the intergalactic space of the local group, are the chemical legacy of the merger They are the merger writing its history into the large-scale distribution of matter in the universe. Long after Milky has settled into its quiet elliptical configuration, the chemical enrichment driven by the starburst will persist in the composition of the halo gas, in the metallicity of the intergalactic medium, in the composition of any future planets that form from gas reaccreted onto the galaxy. The starburst does not just make stars, it makes chemistry. It enriches the universe. This process, supernova feedback driving gas out of star-forming regions, is one of the primary mechanisms by which galaxies self-regulate their star formation. A starburst consumes gas rapidly, and the supernovae it produces heat and disperse the remaining gas, reducing the fuel available for further star formation. The starburst thus contains the seeds of its own termination. This is why even the most intense starbursts in the universe are temporary. The gas is consumed, heated and expelled on timescales of tens to hundreds of millions of years, after which the star formation rate drops dramatically. The merged galaxy, after its collision-triggered starburst, will find itself significantly depleted of cold gas, the raw material for star formation, and will transition to a phase of quiescence in which very few new stars form. It will become what is called a red and dead galaxy, a massive elliptical galaxy, dominated by old red stars, its star-forming days largely behind it. This is the fate of Milky Way, not a death, but a transformation. Not destruction, but a coalescence into something larger, calmer, more massive, and in many ways grander than either of its progenitors. A massive, elliptical galaxy, possibly one of the most massive in the local group of galaxies, rivaling or exceeding M87, the giant elliptical at the centre of the Virgo cluster, that harbours a 6.5 billion solar mass black hole, rotating slowly, its stellar orbits randomised, its gas mostly consumed or expelled, its star formation largely quenched, orbiting in the gravitational landscape of the local group with a combined mass of 2 trillion stars. Now let us ask the question that is most personally relevant to any reader of this script, the question that makes the abstract concrete, that brings the cosmic down to the human level. What happens to Earth? What happens to our solar system? What happens to life, if there is life here 4.5 billion years from now, and if that life is watching? The answer begins with the Sun. The Sun, 4.5 billion years from now, will not be the Sun we know. It will be significantly brighter. Main sequence stars increase in luminosity as they age, as the helium ash building up in their cores gradually makes them slightly more compact and slightly hotter, which increases the energy output. By the time the Andromeda collision begins, the Sun will be perhaps 35 to 40% more luminous than it is today. This increased luminosity will have profound consequences for Earth long before Andromeda arrives. Climate models suggest that the increased solar luminosity will make Earth's surface temperatures rise to the point where liquid surface water becomes unsustainable. Runaway greenhouse effect, within perhaps 1 to 2 billion years. The oceans will evaporate. The water vapor will escape to space, dissociated by ultraviolet radiation. Earth will become a dry, hot, geologically active, but biologically barren rock, its surface temperatures comparable to Venus, long before Andromeda's light begins to dominate the sky. In the more distant future, roughly 5 to 6 billion years from now, the Sun will exhaust the hydrogen fuel in its core and expand into a red giant, swelling to perhaps 200 times its current radius, engulfing Mercury and Venus, and possibly Earth, depending on the precise modelling of the Sun's mass loss during the red giant phase. The Sun will then shed its outer layers as a planetary nebula, leaving behind a white dwarf, a dense Earth-sized remnant of carbon and oxygen, slowly cooling over billions of years. This process, the Sun's own death, is entirely independent of the Milky Way Andromeda collision. It is driven purely by the Sun's internal fuel consumption, and it happens on a similar timescale, overlapping with the early phases of the galactic merger. So the honest answer to what happens to Earth is that Earth will likely not exist as a habitable planet by the time the Milky Way and Andromeda first make contact. Life on Earth, in any form resembling what we know, will almost certainly be extinct well before the merger. The sun will be too bright, the oceans will be gone. The merger event will occur in the context of an already dead Earth, a solar system transformed by the sun's evolution, a planetary system unrecognizable from its current state. But the solar system, the sun as a white dwarf, surrounded by the charred remnants of its planets, will persist. And it will be carried along by the dynamics of the merger, its position in the galaxy changing as its orbital parameters are perturbed by the fluctuating gravitational field of the collision. The white dwarf sun might end up anywhere in the merged galaxy. It might remain in roughly its current orbit, or it might be flung into the outer halo, or it might fall deeper toward the merged center. The probability distribution is spread across a wide range of outcomes, and none of them is predictable for a specific system like ours without knowing the exact initial conditions to a precision that is not currently achievable. But there is another question lurking inside this one, and it is the more philosophically potent question: what happens to life in the universe during the merger? Not necessarily life on Earth. We have established that Earth's biological story is almost certainly over long before the collision. But the galaxy, even now, contains hundreds of billions of planets. Many of them are older than Earth. Many of them may harbour life, or may harbour life's successors, or may harbour civilizations that have been running for billions of years before the collision begins. What does the collision mean for them? The collision is mostly harmless, in the same way that the ocean is mostly harmless to a fish. The gravitational chaos of a merger, the scrambling of stellar orbits, the displacement of stars from their current positions, the creation of tidal streams, is dramatic on galactic scales and imperceptible on planetary scales. A star whose orbit is perturbed by the merger over millions of years does not notice the perturbation on the timescale of years. The change in its orbit, measured over a human lifetime, would be immeasurably small, a slight drift in velocity, a barely measurable change in trajectory. Planets orbiting that star feel nothing. Their orbits are governed by the star's own gravity, which overwhelms the galactic scale gravitational fluctuations by many orders of magnitude. A planet orbiting at 1 astronomical unit from its star, but the Earth-Sun distance, is in a gravitational environment dominated by the star at the 10^1 second to 1 level compared to the tidal influence of the merging galaxies. The merger is invisible to the planet. The planet continues orbiting. Life, if it exists, continues. The one exception, the one mechanism by which the collision could directly threaten inhabited planetary systems, is a close stellar encounter. If another star passes within a few light years of our solar system, its gravity could perturbate the outer solar system, destabilizing the orbits of distant comets and potentially sending a comet shower toward the inner planets. The probability of such a close encounter during the merger is increased compared to normal galactic conditions because the stellar density in the collision zone where the two disks interpenetrate is temporarily doubled. But doubled still means astronomically low, and the probability that any specific planetary system experiences a close enough encounter to meaningfully disturb its inner planets remains very small,
perhaps a few percent over the entire duration of the merger. For most inhabited planets, the merger is not a catastrophe. It is a show, a spectacle, the most magnificent visual event imaginable, written across billions of years of sky. And what a show it will be for any civilization that exists to watch it. Imagine looking up from the surface of a planet somewhere in the merged system, perhaps a billion years after the first contact, during the chaotic multi-pass phase of the merger. The sky is extraordinary. Where there was once a single band of the Milky Way arching across the heavens, the plane of our galaxy's disk, visible as a concentrated stripe of stars, there is now a riot of structure. Stars in all directions. Tidal streams arcing across the sky. Regions of intense blue-white light where millions of newly formed massive stars blaze before their brief lives end in supernovae. Occasional supernovae themselves, visible in daylight for weeks, during the peak starburst phase of the merger, the rate of supernovae in the combined system might be hundreds per century, compared to perhaps 1 or 2 per century in the normal Milky Way. Multiple supernovae per decade might be visible to the naked eye at peak starburst. Pillars of gas and dust, lit from within by newly ignited stars, visible as glowing nebulae spanning the field of view. And in certain directions, toward whatever the combined galactic center looks like at that phase, with 2 massive concentrations of stars approaching merger, a glow of extraordinary intensity. The combined light of billions of stars concentrated toward the core of the forming Milky. This sky has no analogue in any human experience. No painting has depicted it. No film has rendered it accurately. The closest we can come is to look at Hubble Space Telescope photographs of ongoing galaxy mergers, the antennae, the whirlpool, the mice, and imagine living inside one of those photographs, inside the chaotic structure, watching it evolve in real time across thousands of generations. That is what the sky would look like from inside a major galaxy merger during the most active phase. The starburst during this phase has another remarkable consequence. It dramatically enriches the heavy element content of the galaxy. Each generation of massive stars forged heavy elements in its core, scattered them through the galaxy in a supernova, and left behind the enriched material as the raw stuff of the next stellar generation. During the starburst, millions of massive stars are born, live their brief finite lives, and explode, all within tens of millions of years. Each explosion seeds the interstellar medium with carbon, oxygen, silicon, iron, and all the other elements of the periodic table. The interstellar medium of Milky after the starburst will be substantially more metal-rich than either progenitor galaxy today. The planets that form from this enriched gas, if any cold gas survives to form new planetary systems after the starburst and the supernova feedback, will be richer in heavy elements than our own Earth. More silicate rock, more iron cores, more complex chemistry. If life on those worlds follows anything like the pattern it followed on Earth, if the diversity and complexity of chemistry available to a biosphere correlates with the abundance of heavy elements in the planetary system, then the post-merger planets might support more complex chemistry than anything that has existed before. The merger is not just a reshuffling of stars, it is an enhancement of the conditions for complexity. It takes 2 galaxies and produces one that is in certain measurable ways a richer substrate for whatever comes next. There is a much grander context for all of this. The Milky Way and Andromeda are the 2 largest members of what is called the Local Group, a gravitationally bound collection of roughly 80 galaxies dominated by these 2 spirals and their retinues of satellite galaxies. Spread across a volume of space
roughly 10 million light-years across. The large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere as bright detached patches of the Milky Way band, are the largest of our satellite galaxies and are already in the early stages of being absorbed by the Milky Way. The Magellanic Stream, a ribbon of neutral hydrogen gas stretching across a vast arc of sky, is the visible signature of this ongoing absorption. By the time Andromeda arrives, the Magellanic Clouds will have been fully absorbed, their stars integrated into the Milky Way's halo and disk. When the Milky Way and Andromeda merge into Milkomeda, the other members of the local group, the Triangulum Galaxy M33, the numerous dwarf galaxies orbiting both large spirals, will eventually be absorbed as well. The local group will coalesce over tens of billions of years into a single massive galaxy at its centre. Milkomeda will then orbit within the larger structure of the Virgo supercluster, a collection of hundreds of galaxy groups and clusters, including the Virgo cluster itself, centred on the giant elliptical M87, roughly 54 million light-years away. On timescales of tens of billions of years, the question of whether the Virgo supercluster as a whole is gravitationally bound, whether its members will eventually merge into a single structure, or whether the accelerating expansion of the universe will pull them apart, becomes relevant. This is where dark energy enters the story. The universe is not just expanding, it is expanding at an accelerating rate, driven by a mysterious component of the universe's energy budget called dark energy. Dark energy, which accounts for roughly 68% of the total energy content of the universe, acts as a kind of repulsive pressure that pushes space itself apart, counteracting gravity on the largest scales. On the scale of the local group, a region whose member galaxies are gravitationally bound to each other and whose internal gravitational forces exceed the repulsive effect of dark energy at these scales, the expansion is irrelevant. The local group, and hence the Milky Way Andromeda merger, will proceed as described regardless of dark energy, but on the scale of the Virgo supercluster, dark energy is already winning. The Virgo cluster itself is receding from us at roughly 1,100 kilometers per second, faster than Andromeda is approaching us, and the accelerating expansion will ensure that the Virgo cluster and the local group are ultimately separated beyond any possibility of future merger. The universe's accelerating expansion is, on the cosmic scale, isolation. Milkomeda will eventually be the largest gravitationally bound structure accessible to whatever inhabitants it might contain, surrounded by an expanding void, the light of distant galaxy clusters increasingly redshifted toward invisibility. The observable universe, apparent to Milkomeda's inhabitants, shrinking as accelerating expansion carries distant structures beyond the cosmological horizon. The merged galaxy, Milkomeda, will, in the very far future, be an island in an expanding ocean. Its past mergers and starbursts, recorded in the chemical composition of its stars and the orbits of its stellar populations. Its future quiet. Its star formation slowed to a trickle as the gas is consumed. Its supermassive black hole enormous and mostly dormant, waiting. There is something almost poignant in this picture, if poignancy can apply to the inanimate processes of the universe. The collision of the Milky Way and Andromeda is, from one perspective, a destruction, the end of two distinct galaxies, two distinct identities, two structures that have been separate and identifiable for most of the universe's current age. The Milky Way has been a disk galaxy for perhaps 10 billion years. It has grown through many earlier mergers. The thick disk of older stars in our galaxy is thought to be partly the product of an ancient merger with a galaxy called Gaia Enceladus, which happened roughly 8 to 10 billion years ago. Before the thin disk and the spiral arms we inhabit were fully formed, the spiral structure we see today, the arms, the bar, the disk, was built partly from the wreckage of that earlier merger. And when Andromeda arrives and the spiral structure is destroyed, when the disk is scrambled and the stellar orbits randomized in the gas consumed, the Milky Way as we know it will cease to exist. It will not die, it will be transformed. Its stars will continue, its heavy elements will persist, its black hole will survive and grow. But the structure, the beautiful ordered symmetric spiral that you see in images of the Milky Way and edge-on views, the grand design that has structured the orbits of 250 billion stars for billions of years, will be gone, and in its place will be something grander, something more massive, something that carries within its stellar population the chemical record of two galaxies' star formation histories, the orbital record of the gravitational chaos of their merger, the material legacy of the starburst and its millions of supernovae, the enhanced heavy element content that makes its planetary systems richer in the raw materials of chemistry. Milky Way will not be a dead galaxy. It will be a massive, relatively quiescent elliptical galaxy. But even elliptical galaxies are not entirely passive. They accrete small satellite galaxies over billions of years. Occasional flurries of gas fall into the centre and trigger brief episodes of activity in the supermassive black hole. Rare gas-rich dwarf galaxy accretions can trigger localized star formation. Milky Way will breathe slowly, but it will breathe. And here is the thing about the question we began with, what happens if the Milky Way collides with Andromeda, that most answers miss. The collision has already shaped us. The Milky Way we inhabit today is not a pristine, unaltered galaxy. It is a galaxy that has already survived multiple mergers. The thick disk of old stars above and below the galactic plane, distinct in its chemical composition and stellar kinematics from the thin disk where we live, is the remnant of the Gaia Enceladus merger. The stellar streams that arc through the halo, the Helmi streams, the Sequoia stream, the structures identified in data from the Gaia Space Telescope, are the tidal debris of smaller galaxies absorbed by the Milky Way over billions of years. Our galaxy is made, in part, of other galaxies. We are, in part, the product of collisions and mergers already completed. The Gaia Space Telescope, a European Space Agency mission that has measured the precise positions and velocities of over 1 billion Milky Way stars with unprecedented accuracy, has effectively allowed us to reconstruct the merger history of our galaxy from the stellar kinematics. Stars that came from Gaia Enceladus moved differently from stars that were born in the Milky Way's original disk. They have different orbital properties, different chemical compositions, different ages. By sorting out these differences in the billion-star catalogue, astronomers have identified the debris of at least 5 or 6 distinct merger events in the Milky Way's past. Each of those mergers was, in its time, a version of what the Andromeda collision will be. Each of them produced tidal streams, triggered star formation, perturbed the galactic structure. Each of them left a mark that we can read, billions of years later, in the motions and compositions of individual stars. We are reading our galaxy's history, its complete merger history, its full sequence of past collisions and absorptions, in data gathered by a spacecraft orbiting the Sun, measuring angles smaller than a millionth of a degree, translating stellar positions and velocities into the autobiography of a galaxy. This discipline is called galactic archaeology, the reconstruction of a galaxy's history from the chemical and kinematic properties of its surviving stars. It works because stars are extraordinarily persistent records. A star formed 10 billion years ago from a gas cloud in a galaxy that no longer exists separately because that galaxy was long ago absorbed by the Milky Way, still carries in its spectrum the chemical fingerprint of the gas cloud that made it. The abundance of iron relative to hydrogen, the ratio of magnesium to iron, the abundance of barium and europium and dozens of other elements, each of which encodes something about the star formation history and chemical evolution of its birth environment. Stars born in small, isolated dwarf galaxies tend to be relatively iron poor, but enriched in certain elements in ways that reflect the slower, less productive star formation of their birth environment. Stars born in the main disk of the Milky Way have a different chemical signature, reflecting the Milky Way's more prolific and diverse star formation history. By sorting billions of stars by their chemical signatures and their orbital properties, the direction and eccentricity of their paths through the galaxy, we can identify clusters of stars that share a common origin. These clusters are the debris of past mergers, still moving through the galaxy in coherent streams, billions of years after their parent galaxy was dissolved. The Gaia-Enceladus merger, the largest merger in the Milky Way's history, happening roughly 8 to 10 billion years ago, left particularly extensive debris. A significant fraction of the stellar halo of the Milky Way, the roughly spherical cloud of old stars surrounding the disk, is thought to have come from Gaia-Enceladus. The merger was large enough to substantially puff up the Milky Way's early disk, thickening it and creating what we call the thick disk, the layer of older, more vertically dispersed stars above and below the galactic plane that is kinematically and chemically distinct from the thin disk where most young stars and the Sun are located. In other words, the thick disk of the Milky Way, the broad layer of older, metal-poor stars that extends several thousand light years above and below the plane, is partly the product of a galaxy collision 8 billion years ago. A merger that happened before the Sun existed has already shaped the structure of the galaxy we inhabit. This is the context in which to understand the coming Andromeda collision. It is not the Milky Way's first rodeo. The Milky Way has survived mergers before, has been transformed by them, has incorporated the debris of multiple smaller galaxies into its structure, has had its disk puffed up and its halo assembled through the accumulated debris of previous events. The Andromeda merger will be the largest such event in the Milky Way's history, larger than anything in the Gaia catalogue of past mergers, large enough to fundamentally restructure the galaxy rather than merely add to its halo. But it is the same process, the same physics, the same kind of event, on a grander scale, producing the same kinds of signatures in the resulting stellar populations, signatures that, if intelligent life exists in Milky-Way a billion years after the merger is complete, could be read from the chemical and kinematic properties of the surviving stars, just as we now read the Milky Way's merger history from Gaia data. Future archaeologists of Milky-Way, if they exist, will be able to reconstruct from the stellar populations of their galaxy the entire sequence of its formation, the original proto-galactic collapse, the early mergers that built the thick disk, the Gaia-Enceladus event that assembled the halo, the gradual growth through satellite accretion, and finally, the great merger itself, the Milky Way Andromeda collision that created the galaxy they inhabit. They will find two distinct populations of disk stars, one from each progenitor galaxy, identifiable by their different chemical signatures and now thoroughly scrambled orbital properties. They will find the tidal stream debris from the first pass-through still coherent enough, perhaps, to be identified as a stellar stream of unusual composition. They will find the chemical signatures of the merger-triggered starburst in the ages and compositions of a whole generation of stars born during the collision. They will read in the geology of their galaxy's stellar populations the entire story we have been telling here, and they will tell it forward to whatever comes after them, as we are now telling it backward, from present conditions to future ones. That's all are in insane times in the place. The Andromeda collision is not something unprecedented for the Milky Way. It is the next chapter in a long story of mergers and transformations that stretches back to the early universe, when the first galaxies assembled from the first gravitational collapses of primordial gas. The Milky Way's been through this before. Not at this scale. Andromeda is the largest galaxy we have ever merged with, larger than anything in the Milky Way's merger history. But the process is the same process. The physics is the same physics. The outcome is the same type of outcome. We know how it ends, because we have seen galaxies at every stage of it, and because we have read, in our own stellar populations, the chemical and kinematic signatures of the mergers we have already completed. A universe does not build its largest structures through pristine, unmerged isolation. It builds them through collision, interaction, and merging, through a hierarchical assembly process in which small things come together to make larger things come together to make still larger things. Galaxies grow by absorbing smaller galaxies. Galaxy groups grow by absorbing individual galaxies. Clusters grow by absorbing groups. This is the cosmic web of structure formation, driven by the primordial density fluctuations imprinted in the universe's earliest moments and amplified by gravity over 13.8 billion years. Our galaxy is part of that web. The Andromeda collision is one step in that web's evolution. The formation of Milkomeda is the universe doing what the universe does, assembling complexity, building larger structures, turning the initial conditions of the Big Bang into the present-day landscape of galaxy clusters and superclusters and cosmic filaments. We are not watching the end of something, we are watching the middle of something. The universe at 13.8 billion years old is roughly a third of its way through the period of galaxy evolution that is relevant to life, the era when stars exist, when heavy elements are being produced and distributed, when planets form and chemistry operates, and whatever processes lead to biology can proceed. The Milky Way Andromeda merger will happen in the universe's middle age, when plenty of star formation remains possible, when the heavy element enrichment of the cosmic web is still proceeding, when the conditions for life and complexity are, if anything, better than they are today. There is a final thought worth holding before we close, and it concerns the perspective from which we have been watching all of this, the perspective of an observer inside the galaxy, looking out. We know about the coming collision. We have measured Andromeda's velocity. We have run the simulations. We know the timeline. We know the outcome. We know what the sky will look like during the merger, what the starburst will produce, what Milkomeda will become.
We know all of this not because we have lived through it, but because we have built instruments sensitive enough to measure galaxy velocities to a part in a million, because we have developed a theoretical framework, general relativity, gravitational dynamics, computational astrophysics, capable of simulating the evolution of systems containing 1 trillion stars over billions of years, and because we have had the imagination and the patience to apply those instruments and that framework to the question of what comes next. But let us sit with something less commonly discussed: what the merger means for the question of life and intelligence on cosmological timescales. We have established that Earth will not survive to witness the collision. The Sun's increasing luminosity will have sterilized the planet long before the first contact. But the universe is not short of planets. The Milky Way alone contains at minimum hundreds of billions of planets, and a significant fraction of those planets orbit stars that will still be burning in stable phases 4.5 billion years from now. Red dwarf stars, the most common type of star in the galaxy, far outnumbering Sun-like stars, burn their fuel so slowly that they will still be on the main sequence, not just in 4 billion years, but in 4 trillion years. Many of the red dwarf stars in the Milky Way today will still be burning when Andromeda is a settled elliptical galaxy, its starburst long quenched, its supermassive black hole dormant, its stellar populations aging quietly through the long galactic afternoon. This matters enormously for the question of life. If life exists on planets orbiting red dwarf stars anywhere in the Milky Way or Andromeda, and we have no particular reason to think it does not, given that red dwarfs are by far the most common type of star, that many of them have planets, and that some of those planets are in the habitable zone, then those forms of life will witness the collision. They will see Andromeda grow in their sky over millions of years. They will see the merger begin. They will survive the first pass-through, undisturbed on their planetary surfaces, the gravitational chaos of the merger utterly imperceptible on the timescale of their lives. They will watch the sky transform, the band of the Milky Way dissolving, as stellar orbits are randomized, the organized spiral structure fragmenting into the chaotic, irregular morphology of an ongoing merger. New bright stars blazing into existence in the starburst regions, supernovae flaring and fading across the sky in the coming years of peak star formation. These hypothetical observers, whatever they are, whatever form intelligence takes on a planet orbiting a red dwarf in a galaxy 4 billion years more evolved than ours, will have a perspective on the merger that we cannot have. They will see it from inside, in real time, with whatever observational capacity they possess. They will know, if they have developed astrophysics, that their galaxy is merging. They will have calculated, as we have, what comes next. They will have simulated the merger and known its outcome long before it completes. And they will have the experience, unprecedented in any civilization's history, of watching their entire galaxy transform around them over the course of their civilization's existence. Not just their planet, not just their star system, their galaxy. The structure that contains them, the cosmic home that has defined the distribution of stars and gas and dark matter within which their civilization has arisen and grown, that structure will change visibly and dramatically. On timescales short enough for a civilization to witness, the merger will take 6 to 8 billion years total, but the most dramatic phases, the first pass-through, the starburst, the multi-pass chaos, will occur over hundreds of millions of years, short enough that a sufficiently long-lived civilization could track them across many generations. This is in its own way a kind of privilege. We are too early for it. We get the prediction. We get the calculation.
We get the knowledge that the merger will happen, what it will produce, what the sky will look like during it, but we cannot see it. The galaxy's most spectacular event is scheduled for an appointment we cannot keep. Our biological descendants, if they exist, will be unrecognizable from us, or absent entirely when it begins. The technology that might allow us to be present for it, to send some representative of human knowledge and curiosity into the long future, does not exist and may never exist. We know the most spectacular event in our galaxy's remaining history, and we cannot attend it. We know, without ambiguity, what we are missing. This is not cause for despair. It is simply the shape of our situation, the specific position in time and space and knowledge that we happen to occupy. Every civilization, if it exists anywhere, occupies such a position, knowing some things and not others, able to see some things and not others, placed at a particular moment in the universe's history, with a particular set of tools and a particular set of accessible phenomena. We happen to be placed at a moment when the Large Hadron Collider exists, when Gaia exists, when LIGO exists, when the James Webb Space Telescope exists, and we happen to be in a galaxy 4.5 billion years before its greatest collision. We can study the merger intellectually, we can know it thoroughly, we cannot witness it. Both of those things are true, and neither cancels the other. We are a species that has existed for perhaps 300,000 years, on a planet 4.54 billion years old, in a galaxy 13.6 billion years old, in a universe 13.8 billion years old. In those 300,000 years, an eye blink by any of those timescales, we have managed to figure out not just what the Milky Way is, not just that Andromeda is a galaxy rather than a cloud, not just that the universe is expanding, but what will happen to our galaxy in 4.5 billion years. We have extended the reach of human knowledge across timescales 15,000 times longer than the entire existence of our species. We have simulated the future of the cosmos with enough precision to make specific, testable, quantitative predictions. We have, in some meaningful sense, seen the future of the Milky Way, not perfectly, not in complete detail, but in its broad outlines, with enough clarity to describe the sequence of events with confidence. That is not a small thing. That is, perhaps, the most audacious thing our species has ever done. Not landed on the moon, not built a particle accelerator, but extended human consciousness so far beyond the immediate human timescale that we can look at a faint smudge in the constellation Andromeda and know, not guess, not imagine, not mythologize, but know, through careful measurement and honest mathematics, that it is falling toward us, that it will arrive in 4.5 billion years, that when it does, the sky will become the most spectacular thing any intelligent being has ever witnessed, that two galaxies will become one, that hundreds of billions of new stars will be born in the collision, that our sun will be somewhere in the merged system, its light still shining even if Earth is long gone, that the two supermassive black holes at the centers of our galaxies will slowly spiral together and merge in a final act of gravitational violence that sends gravitational waves through the fabric of space-time itself. We know all of this. It is written in the light from Andromeda, decoded by our telescopes, processed by our mathematics, held in the minds of astrophysicists working quietly in offices and observatories scattered across this small and temporary planet. The collision will come. It will be extraordinary. And long before it arrives, we will have had the chance, if we are careful, if we tend our curiosity, if we build the next generation of observatories and train the next generation of astronomers, to understand it in still greater detail. To know, not just the broad outline, but the specific trajectory of the two galactic cores, the exact rate of the starburst, the precise final mass of the merged black hole, the detailed distribution of stellar populations in the merged galaxy, millions of years after the coalescence. The knowledge will grow even as the collision remains distant, because the universe broadcasts its intentions in light and gravitational waves, and we are learning, year by year and instrument by instrument, to listen more carefully. The universe is patient. It has been running this experiment, galaxy formation, merger and evolution, for 13.8 billion years, and will continue it for trillions more. We have had, in our brief moment of wakefulness, the extraordinary fortune to exist in the universe, where the laws of physics are uniform, where the same equations operate everywhere, where the light from a galaxy 2.5 million light years away carries in its Doppler shift the message that the galaxy is falling toward us, where the instruments and mathematics exist to decode that message is below the science. We need to see pyramids of galaxies become more or less pyramid. We need to see all civilizations waiting for us, or walking. And where there are minds curious enough to ask what it means. Look up at Andromeda on a clear night. You know what that smudge is. You know what it is doing. You know what it will become, and what you will become, what your atoms will become, scattered through the interstellar medium of a merged galaxy that your galaxy helped build. It is not a threat. It is not an end. It is a rendezvous, written in the laws of gravity, kept by two galaxies across 13 billion years of cosmic time, arriving with absolute certainty in the fullness of a future that is longer than the current age of the universe. The two galaxies have been falling toward each other since before the Earth existed. They will complete the fall long after the Earth is gone. And in the merged galaxy that emerges, that massive, heavy element enriched, slowly breathing elliptical that was once two spirals, now one, the stars that were ours will still burn, orbiting in changed paths through a changed galaxy. And the physics that made this collision predictable from a small blue planet 13 billion years into the universe's history will still operate, as it always has and always will, patient and precise and entirely indifferent to whether anyone is watching. The collision is not the end of anything. It is the universe, doing what the universe does, building, always building, out of collision and chaos, and the patient arithmetic of gravity, something larger than what was there before.